Hello, my name is Joseph Shackelford, and this is my Lab 4 on circuits and capacitors. In this lab, we predict the behaviors of circuits containing resistors in series and in parallel, and use tools such as a multimeter to measure actual values of potential differences in conventional current. The purpose of it was to better understand current and potential in real applications and to have a hands-on experience with resistance and circuits. So the results that I found was my current found from my predictions was accurate when compared to reality, and in an RC circuit, the magnitude of current is time-dependent. So the principles used are the conservation of energy and change, Kirchhoff's circuit laws, and Ohm's law. So assumptions we made was resistance of wires is negligible, and resistance of the ammeter is negligible. So experiments and observations is a system is everything in the circuit and surroundings is everything else. Units of conditions are two 1.5 volt batteries and two light bulbs, which act as resistors, and an ammeter. I predicted that I1 equals I2, and the total resistance equals 47 plus 100, which is 147 ohms. The current equals V over R, which is equal to 1.5 plus 1.5 over 147, which is equal to 0.2 amps. And the readings actually was around 3 volts. So now we're looking at the potential differences at different points. We're looking at points A, B, C, D, E, F, and G. So at point B to point A, the potential difference is 3 volts. From C to B, it's 0 volts. From D to C, it's 0.96 volts, negative 0.96. From E to D, it's 0 volts. F to E, negative 2.04. And for the rest, it's all 0. If you add all this up, the total difference, total change is 0, which follows the loop rule. So here's a graph of the total potential difference. Here it is right here. You can take a look. It increased, obviously, from the battery, the EMF, and then it decreased through the resistors, and it eventually ended back at 0. So now we're looking at an RC circuit, which we built. It has a 10 ohm bulb, a 9 volt battery, and a 20 millifarad capacitor. So the bulb starts out bright when initially connected, and it slowly loses charge. And when the battery disconnects, the bulb lights up again, but it quickly goes out. So model discrepancies and sources of error. There were likely many mistakes. Since we were using like a less than optimal setup in the lab, and we weren't given much instruction on how to use the tools, there might have been many mistakes, calculation errors, such and such. And the light bulbs are of unknown origin, so we kind of had to guess the resistance. Yeah. So what ifs and whys? So what if we'd been lab in real life and use the actual ammeter instead of an ideal ammeter? How it affected? Well, since we used the actual ammeter, it did add resistance, and our red current was lower, but we kind of adjusted based off our calculations. And once again, if we're doing it in real life, and use a real battery charge or capacitor with no resistor in the circuit, how quickly would the ideal model charge? It charged much faster with no resistor, but since there is resistance on the wire, it's not instant. And conclusions that were made, the node and loop laws are extremely fundamental to analyze circuits, and resistors and capacitors change voltage and current within the circuit as time goes on. So yeah, thank you.